Morning. Today we discuss what are heterojunctions. A heterojunction is defined as a junction formed between two dissimilar semiconductors. The energy band diagram of two isolated pieces of semiconductors prior to the formation of a heterojunction are shown over here in this diagram. Two semiconductors are assumed to have different energy band gaps, e.g., different dielectric permittivities Es, epsilon s, different work functions q phi s, and different electron affinities q chi. The work function is defined as the energy required to remove the electron from Fermi level EF to a position just outside the material, the vacuum level. The electron affinity is the energy required to remove an electron material from the vacuum level. The electron affinity is the energy required to remove an electron from the bottom of the conduction band EC to the vacuum level. The difference in the energy of the conduction band edges in the two semiconductors is represented by delta EC, and the differences in energy in the valence band edges is represented by delta EV. So we can see it in this diagram, that is delta EC is equal to Q chi 2 minus chi 1, or delta E psi is equal to Eg1 plus Q chi 1 minus Eg2 plus Q chi 2, that is equal to delta Eg minus delta EC, where delta Eg is the energy band gap difference between delta Eg is equal to Eg1 minus Eg2. This figure shows the equilibrium band diagram for an ideal abrupt heterojunction formed between two semiconductors. In this diagram, it is assumed that there is a negligible number of traps or generation recombination centers at the interface of the two dissimilar semiconductors. We note that this assumption is valid only when heterojunctions are formed between semiconductors and with closely matched lattice constants. Therefore, we must choose lattice matched materials to satisfy the assumption. For example, the AlXGA1 minus X AS materials with X ranging from 0 to 1 is the most important material for heterojunctions. When X is equal to 0, we have gallium arsenide with band gap of 1.42 electron volts and a lattice constant of 5.65 angstroms at 300 Kelvin. When X is equal to 1, we have AlAs with band gap of 2.17 electron volt and a lattice constant of 5.6605 angstroms. The band gap for ternary AlXGA1 minus XAS increases with X. However, the lattice constant remains essentially a constant. Even for the extreme cases where X is equal to 0 and X is equal to 1, the lattice constant mismatch is only 0.1%. There are two basic requirements in the construction of energy band diagram. The Fermi level must be the same on both sides of the interface in the thermal equilibrium, and the vacuum level must be continuous and parallel to the band edges. Because of these requirements, the discontinuity in the electron band edge delta EC and the valence band edge delta EV will be unaffected by doping as long as the band gap Eg and the electron affinity Q chi are not functions of doping. That is, as in non-degenerate semiconductors, the total built-in potential VBI can be expressed as VBI is equal to VB1 plus VB2, where VB1 and VB2 are the electrostatic potentials at equilibrium in semiconductors 1 and 2 respectively. Under the conditions that the potential and the free carrier flux density, defined as the rate of free carrier flow through a unit area, are continuous at the heterosurface, we can derive the depletion widths and the capacitance from the Poisson equation using the conventional depletion approximation. One boundary condition is the continuity of the electric displacement, that is epsilon 1 E1 is equal to epsilon 2 E2, where E1 and E2 are the electric fields at the interface X is equal to 0 in the semiconductors 1 and 2 respectively. VB1 and VB2 are given by the value of VB1 and VB2, they will be given as epsilon 2 N2 VBI minus V divided by epsilon 1 N1 plus epsilon 2 N2, and VB2 is equal to epsilon 1 N1 VBI minus V divided by epsilon 1 N1 plus epsilon 2 N2, where N1 and N2 are the doping concentrations in semiconductors 1 and 2 respectively. The depletion widths X1 and X2 can be obtained by the values. X1 is equal to under root of 2 epsilon 1 epsilon 2 N2 VBI minus V divided by Q N1 in brackets epsilon 1 N1 plus epsilon 2 N2 bracket close, and X2 can be written as under root of 2 epsilon 1 epsilon 2 N1 VBI minus V bracket close divided by Q N2 epsilon 1 epsilon 2 in brackets plus epsilon 2 N2 bracket close. So these are the values of the depletion layer widths which we have obtained. Thank you.